Good morning. You all know me by now. I'm Tim. I'm the lab technician, and we're going to be discussing this morning the refrigeration side troubleshooting form. Now you're going to encounter this in the course 231, BCT 231. Now this form you may or may not use out in the field, but it's going to give you the knowledge that you need to know so that you can properly troubleshoot AC units. Now this is only residential units, and it can involve your regular air-to-air, air-to-water units that you will encounter, and to include the heat pump units. Now what we are going to discuss is two things. One, we're going to talk about the actual readings and the typical readings. Now, nowhere have you seen anything about this yet up to this moment. If you research it in your ARI textbook, you will run across this. But in your NCEER textbooks, you will not. But this is a very helpful tool for the typical residential service tech to help him or her get through and troubleshoot the problem. If it's mechanical, that's one thing. This is more on the refrigeration side of it that will help you troubleshoot this. So let's start off. First, you need to know, and this is where your senses come into play. You've heard about it, you've done a few exercises in it, but this is where it's all going to boil down to. I can only inform you of what to do. You have to learn to memorize these steps. So when you come upon a unit, the first thing you want to find out is, what refrigerant am I dealing with here? That's going to be important, because when you go out to these units, you're going to either deal typically with R22, or if it's a newer unit, it's the 410A. Now, 410A is also going to be called different things by different companies. So you cannot just sit there and think R22, 410A, everything's happy. That's not going to be the way it's going to be. Suva, DuPont, all make their own brands on this. They should be called 410A or R22, but they may have their own nomenclature. And remember, it also deals with how you work with that refrigerant. Some cans are upright, other cans are upside down. So now, this is a form that we're going to give you. I would highly suggest that you Xerox these off to help you, the tech, solve some of your problems out here. First of all, we're just going to explain some of the form to you so that you understand. Let's just start at the top. You're going to see refrigeration troubleshooting form. You're going to see the different refrigerants, and of course, if the refrigerant that you're working with isn't on here, fill it in. This is going to help you out if you ever have to return to the unit. You staple this to your service copy that you're going to bring back home to the office so that you have it available for the next tech. The next thing is entering air. Well, you notice that it's pointing towards the condenser. Now, when it's pointing towards the condenser, unless I'm wrong or somebody knows something different, condensers are located where? And the answer should be outside. It may be a rooftop package unit, or it may be a split system. If it's a split system, the condenser is going to have to be outside. Now, if it's a heat pump, it's going to be called what? Outdoor unit, indoor unit for the evaporator. Outdoor or indoor, depending on if it's a heat pump. So now we've got the entering air at the condenser. Now the entering air is that air that is being sucked in through the coils of the condenser. That's the dry bulb, and to do that you just need a thermometer. So you're going to need to place that thermometer up next to the entering air of the condenser. The wet bulb, of course, you're going to need to have either electronic sling psychrometer or the old-fashioned whip type sling psychrometer, which you're going to practice on both of those in here in the lab if you haven't already. So that's the condenser. Now, you're going to also take what is known as your high side discharge pressures from your gauges, your manifold gauges. And depending on what type of unit it is, it'll determine where you're going to take that. So you're going to take the high side discharge pressure, and there is what is known as typical and actual. All we're dealing with right now is the actual. And you notice that it's in PSIG, and you have to convert it to a temperature, and this temperature should represent the saturation temperature. Now, the saturation temperature can come from your pressure using your PT card, pressure temperature card, to get that temperature. That temperature is the saturation temperature. Saturation temperature means only one thing: that temperature at which it either begins to change, it begins to change state, but it either changes from a vapor to a liquid, as in the condenser, or in the evaporator as a liquid vapor to a total superheated vapor. So it depends on which part of the unit you're working on. You have to understand that concept. We come down here, we got the evaporator, another major component. The component, or the evaporator, is going to have both entering air and leaving air. Now, your leaving air, you want to take, again, the dry bulb and the wet bulb at the nearest location of the vent coming out of the ductwork. Now, it may be in the hallway, maybe the first bedroom that you come to, the bathroom, whatever. You want to take that dry bulb and wet bulb again, all right, and fill it in at that location. The entering air is normally your return air. It will be on the floor. There may be more than one ductwork for the return air. All right. So again, return air, or entering air, excuse me, and your leaving air. Entering air, another name is return air. Dry bulb, wet bulb. Then we come over to the low side suction pressure. Again, you're going to take that from your manifold gauge. We are not worried about the typical at this point. We're worried only about the actual. The PSIG, again, it'll take your low side pressure. You will convert it to a temperature from using your PT card. Now, your suction temperature, and whenever you see this symbol, at, that means you're physically taking a reading. That means that you're taking a temperature probe of some sort and attaching it to the line and taking an actual reading. At the compressor, now as you've read in your books, at the compressor doesn't mean you shove it up against the compressor. It means that it's 4 to 6 inches away, and preferably you will take that and use it as your actual reading. All right, now to do that, you need the temperature probe. A handheld thermometer will not be accurate because you got too much ambient air around there. And while we're on that, what is ambient air? Ambient air is that air that is around an object, i.e. a motor. You have ambient air around a motor. Pipes, you have ambient air around those pipes. So you have to close that off. And the way to do that is wrap it with some sort of insulation tape. When you do that, you cut out the ambient air and you get right to the exact location and you get an accurate reading. All right, so we've discussed the low side, the high side, the suction pressure, suction temperature at the compressor. All right, we've talked about the entering air, the leaving air on the evaporator. We've talked about entering air in the condenser. We've talked about the high side discharge pressure. Now, again, the liquid temperature at condenser. Now, over the period of however long you've been in the program, we've emphasized that you need to know these terminologies. This is where this is so important, because you have to understand, it's just like going down to Mexico, and if you're not speaking their language, you're not going to be able to communicate. The same theory is put here. You go out to the field and you can't talk their language, you will not be able to convince somebody that you understand what you're talking about. That's not saying, unfortunately, the tech that you're talking to will understand what you're saying, because they may not have learned the proper terminology. So pass that on while you're out there. So the liquid temperature at, again, at, meaning a physical temperature reading at condenser. Now you notice that the arrow is pointing right at the outset of the condenser. So again, you need to know your lines, you need to know what they're called, where they're located, and how to track them down. Because units are going to be in all types of different configurations. All you have to do is know where the compressor is and understand what the flow refrigerant is, and you can sort out all these lines. It doesn't matter if you've never seen that unit, or if I bring you over to the boiler plant here and tell you to track down the lines. All you have to do is find the compressor, and everything else is second to none. So again, be a couple inches away, because now this is your liquid line, remember, going to your metering device. So what you are trying to do is get the liquid temperature. Now, of course, common sense tells us we can't drill a hole in there and get the liquid temperature. But engineers along the way have figured out that, hey, look, if the refrigerant liquid is flowing through here, your pipe temperature is going to be a certain temperature degree. So hopefully, as this refrigerant flows through your condenser, remember it is desuperheating because it's a superheated gas at this time. It's starting to condense somewhere down through this condenser, and we don't care. And then eventually it's going to come out as a subcooled liquid. So the three things that go on is desuperheats, condenses, subcools. It comes out as a high temperature, high pressure, subcooled liquid. This is what we want to take the temperature reading from. Again, 4 to 6 inches away from the outlet of the condenser. Wrap it, secure it with some sort of insulation tape so that you have a good solid reading on your meter. Now, the other problem that you're going to run into, and in this classroom, when you do that original reading on this, your unit, you have to take the cover panel off, locate your liquid line and your saturation temperature line or suction line, find those two lines, put your meter and tape it in there, and then cover up the cover back on there before you can hook your gauges to your unit. So every unit is not the same, and you're going to experience that out here in the field with our units. Some are very easy to get to, some are very complicated. All right, it just depends on the manufacturer. All right, so we've discussed all of this area except for the metering device. Now the metering device is not going, especially in residential units, unless it's a heat pump, will not stand out. It's going to be buried in that liquid line somewhere. But you can definitely tell yourself and remember that somewhere between 4 to 6 inches back from the inlet of the evaporator is going to be a metering device. It's either going to be a TXV, which you should automatically know, an automatic expansion valve that you're aware of, or it's going to be some sort of fixed metering device. Now that fixed metering device could be anything like a capillary tube or a piston type, which you're not going to see because it's inside that line. So understand the metering device, if it's not physically visible 4 to 6 inches back, you're going to know at least somewhere in that line at the manufacturer they put a metering device in there. And the reason they do that is because it's more economical and cheaper in the long run than to put the TXV. That's how they cut down on the prices. The other thing that you're going to run into is our evaporator, and we've already discussed this. And the evaporator does two things. It evaporates and it creates superheated gas. All right? So we've now discussed this whole process. And the compressor, that can be any type of compressors. You may have one compressor, you may have two compressors. You may have one small compressor and a larger compressor. You may have a scroll compressor, or you may have what is known as a hermetically sealed compressor. This is in all your residential units. Again, depending on who you're buying it from or who makes the product. All right, now we come down to this location down here where you're going to start filling in the numbers. Again, all we're going to be discussing right now is your actual readings, just your actual readings. So you come down here for the conditions, typical and actual. For easy accessibility for yourself, pay attention what side you're working with. We're only dealing with the actual right now, only the actual. So outdoor air temperature, now common sense tells you you're going to go back out to your outdoor condenser unit and take the reading, I don't know, 3 or 4 feet away from the unit if you can. You're going to take that reading, and it's going to take a minute maybe for your unit, your metering device to acknowledge what the temperature is, depending on if you came from a very cold room to the outside, so don't be in a hurry. Certain things, this whole chart is based off of one thing, what is known as your typicals. And we're going to go into that here shortly. But as for this, we're off of this portion of it, we're only going to deal with the typical, or the actuals right now, the actuals. The indoor air temperature, where are you going to get that? You're going to get that from your leaving air. So stand back a few feet from the unit, the ductwork, and take an actual reading of the room temperature. Then we've already discussed all of the other readings, and by now you should already know how to get your superheat and subcooling, but we will go over that again for reminders. You're also going to need to know your compressor amps, your outdoor fan motor amps, and your indoor fan motor amps. This plays a part when you start to troubleshoot and use your, what we call here, the idiot card wheel, all right, because it's going to play a part into figuring out if it's overcharged or undercharged or what so. So please pay attention and be careful when you're taking these readings. You're going to use your amp meter to take those 3 readings, and be sure that you don't stick your fingers in the fan blades or anything else so that nobody gets hurt. And now we've done the overview, now we're going to start throwing numbers in here. And these numbers become very important when you're trying to troubleshoot the unit. We will start at the top here. We're dealing with R22. Everything in this classroom will either be R22, 134A, or 410A, depending on what unit you're working with. But for simplicity, it's R22. The first thing we're going to do is hook up our gauges to our low side and high side, run the unit for 15 minutes. When that happens, you're going to look at your gauges, and you're going to take the pressure reading from your high side. In this case, we'll say it's 270 psig. Now, the 270 is a constant pressure in the high side. But we need to fill in the bottom down here, which is your saturation temperature. To do that, you must use your PT card. You look under R22, and all these cards are a little bit different, so just find R22, scan down, and find what is ever closer to 270 psig. In this case, it looks like 274, and it's between 120 and 124 degrees. So that 120 and 124, we'll just, for argument's sake, say it's 122. Because you're going to try to split hairs here. Just try to round it off, make it easy. That's the high side. All right. Now we want to do the low side. The low side's the same way, except this time we'll say it's 70 psig. Go look in your PT card, find 70 psig, read down, go to the left, and you'll find the saturation temperature, which is about 40 degrees. Now that 40 degrees and that 122 degrees are known as saturation temperature degrees. That is the degrees in which at that point the refrigerant is beginning to change state. May it either be in liquid to vapor form or a vapor to a liquid form. So that's what saturation temperature means. We know how to find our pressure temperatures, or pressures, from the gauges. Now we'll go and we'll look at our metering device. In this case, to make it simple, we're going to just use a fixed metering device. We have fixed, and fixed are things like your capillary tube, your piston type driven metering devices, TXVs, automatic expansion valves. Those come with either heat pumps or higher end units. In the classroom, we'll use mostly fixed units. Now we need to go and say, well, our outside air temperature is 95 degrees. Our wet bulb is 40 degrees. You're going to find that using the sling psychrometer, and you're going to go outside to your condenser area, and you're going to retrieve those numbers. Now, don't go right up on top of the unit. You can stand back a foot or two and collect your dry bulb and your wet bulb. Now, those numbers are always going to be changing depending on the time of day or whenever you're going out there to do your task to fix the unit. So we're just using those numbers as for the classroom conversation. And then you'll see where that plays a part in the rest of this form later on down the road here. Now, the liquid temperature at condenser. The liquid temperature means just that. The liquid of that refrigerant inside that pipe. Now, we can't measure the liquid inside that pipe. But engineers have figured out that because this is copper and because you put the thermometer outside and you protect it with some sort of insulation tape, you're going to get a give or take reading pretty close to what you should be getting if you were inside that pipe. So we'll just say, we'll say that it's 120 degrees. Whoops, excuse me. See, that's where you got to be careful. You got to pay attention to what you're doing here, because if you put it in the typical, you're going to have it hinder you later on down the road. So 120 degrees. And remember, your tape has to be, the insulation tape around your pipe for your thermometer has to have a good contact. So you want to ensure that you got a really good contact. Just don't slide it up underneath some foam insulation and think that's going to give you your temperature. You'll be surprised. The other thing is, we'll come over here to the low side and the suction temperature at the compressor. Now, don't go right up on the compressor. Stand back 4 to 6 inches, all right? And place your thermometer. Again, wrap it again so you protect it. And we'll just say that it's 55 degrees, all right? Oh, did it again, didn't I? All right, actual. We're dealing with actual only, all right? So 55 degrees. Now, most of our measurements have been taken for the situation except for the evaporator. So we go in the house, and you're going to go preferably to the nearest register to your heat exchanger and air blower. You know, it could be in the hallway, but it's typically one of the bedrooms or the bathroom. Preferably get a larger vent so you get a true reading. But we'll say that that it's blowing out 70 degrees. So you go to the register, put the thermometer, electronic thermometer up near the register. You know, it depends on the caliber of measuring device you have. 30 seconds, you'll get a true reading. So we'll say that it's 70 degrees dry bulb and 45 degrees wet bulb. Now this is the air, or better known as the supply air, that's leaving. It's coming out into the occupied space. That's the leaving air. The entering air is those registers or diffusers that are on the bottom of the floor, inlets near the unit, the air handler itself. It's returning the air, entering air, another name for return air. So that temperature, we'll say, is 75 degrees and a wet bulb of 52. So now we look at our sheet and we see that we know what the refrigerant is. We check all the areas to be sure that they're in the actuals. High side discharge, actual. Outside air temperature, dry bulb and wet bulb. Our actual for our liquid temperature at the condenser. Entering air, dry bulb and wet bulb. Dry bulb, wet bulb leaving air or supply air. This is your return air, supply air. We know we got a fixed metering device. We know our low side suction pressure is 70 with our saturation temperature being 40. And we know that the suction temperature at compressor is 55 degrees. So we know, and it's all in the actual, so we know we have it all taken care of. So the first thing I want to do is come down to my sheet at the bottom and fill all this out. My outdoor air temperature is 95. My indoor air temperature is 70. My discharge pressure, now remember, now everything else will be either typical or actual here. So I want to be over my far right side. Discharge pressure, 270 psi. My saturation condenser temperature, which is 122. My liquid temperature at condenser, meaning that you're physically taking a reading, is 120. My suction pressure, low side, is 70 psig. My saturation suction temperature, all right, is 40 degrees. And my saturation, or my suction temperature at compressor is 55. Now, we need to figure out superheat and subcooling, all right? So the first thing is, superheat is found only in the evaporator. So how do we go about figuring that out? Well, you're going to take your suction temperature at compressor, which in this case is 55 degrees, and you're going to subtract your saturation condenser, saturation temperature for your evaporator, which is 40 degrees. Here it gives me a 15 degree superheat. Now, it all depends on the books that you're reading at the time, but typically it can range from 5 degrees to 40 degrees. In the school environment and out in the real world, if you can get between 10 and 15, 10 and 20, that'll give you what is known as a ballpark figure to work with. If you're so fortunate that on the unit that you're working with, and you can find the dry bulb and the wet bulb and the pressure chart on that, then go with that. That's the manufacturer. You always want to go with that. But this is like the best thing to that. Now, remember, superheat is only found on the evaporator side. Your subcooling, on the other hand, is found on your high side. Again, you gotta figure out what numbers you're taking from where. So we want 122 in this case, which is our saturation temperature, to our liquid temperature at condenser. In this case is 120 degrees. So we only have 2 degrees subcooling. Well, for this benefit, we want that to be somewhere between 15 and 20. But all I'm interested in you understanding is how and where to put all these numbers at and what they all mean, because it's going to play a vital part in the next phase of this. Your compressor amps, your outdoor fan motor amps, and your indoor fan motor amps are all taken using your amp probe on the particular wires. All right? You will have to physically look at the schematic and figure out where your, quote, hot wire is, or the power wire for that element, and connect your amp probe to that and get a reading. Now remember, this becomes vital and you're going to need to have that information later on. I think everything has been covered up to this point so that you fully understand what is being asked of you on the actual side of the house. All right? You're going to fill this out numerous times, so it's going to become repetitious, but be sure that when you get out into the field you do this, and it'll make your troubleshooting techniques a lot easier. Now it becomes important to know, what do I compare this with? Well, that's all fine and dandy if I go out on a 95-degree day. But remember, your season startups normally do not happen in mid-July. They normally happen in April, May timeframe when it isn't 95 degrees. So what we need to do is we're going to change a few things here. We're going to change the outside air temperature, and for this particular exercise we're going to use 70 degrees with 30-degree wet bulb. Now, what do you notice already? This number and this number will change depending on the situation that's occurring on the field. All right? So before we had 95 degrees and these numbers. Well, we're just saying it's a 70-degree day and you still got these numbers off of your unit. That's perfectly okay. What becomes important is, how do you go find the typical? And what do I do with the information from typical and actual? Well, let's just start through this process. And our typicals will be in red for this exercise. This board is located out in the lab for you to work with. So anytime you have questions, refer to this lab sheet out there on the wall. You will also have copies in your folder or your packet that you have with you. Again, this is a great tool when you go out in the field and start troubleshooting. But up here, the dry bulb plus 30 degrees equals typical saturation temperature. Now do you understand why we all need to be on the same terminology? Because I'm going to be talking this terminology, and if you don't understand what typical saturation temperature is, or saturation temperature, we have a problem. So at this point, you need to know what all those terms mean at this present moment. So our dry bulb in this case is 70 degrees. We'll just put that up here. It says plus 30 degrees. Now that's a standard. All right. So, and understand another thing. This is not for high efficiency units. And when I'm talking high efficiency, I'm talking about units that are like 16 and above SEER. You can use this on 13, 14 SEER and below, but don't try it on 16 or 18 SEERs. So we got now 100 degrees of saturation temperature. Well, remember, we're looking under typical, and I have to put it under the saturation area. In this case, it's 100 degrees. Well, then you ask yourself, well, where do I get the pressures? Well, the pressures are found by reversing the operation on your card. Now you're going down the left-hand side of the column. You're going to find 100 degrees, move over to your right under R22, and it's 195.9 degrees, or for simplicity, we'll say it's 196 psig. Now, you notice that we're starting to have a problem here. We took off our gauges 270 psig, but my mathematical formula tells me it should be reading 196 for a 70-degree day. Well, that sends up some red flags. And that's what this whole chart is about, is to help you understand what's going on. The next thing we want to do is come over here to our liquid temperature at condenser. My little cloud says typical temperature will be 10 to 15 degrees lower than the typical saturation temperature. Well, my typical saturation temperature is 100 degrees. Therefore, I have to be 10 to 15 degrees less. And for argument's sake, we'll just use 15 degrees. So now I should have a temperature of 85 degrees in my typical. And the reason being, what are all these numbers meaning? Well, simple. Remember, it says 10 to 15 degrees lower than your saturation temperature. Saturation temperature is that temperature at which it begins to change state. In our condenser, we are going from a superheated gas to a subcooled liquid. To do that, I need 15 degrees, anywhere from 10 to 15 degrees temperature difference, to ensure that when it comes out here to the metering device, it's 100% liquid. And if some engineer, some chemical engineer, I guess, figured out that if you subtract 10 to 15 degrees of heat from that refrigerant, it will automatically become liquid through that process. So that's where that 15 or 10 to 15 degrees comes from. So now we have our typicals for this side of the house. We're going to go do the same thing for the suction side or the low side of the house. The first thing I want to do is come down here. My leaving air minus 15 to 20 degrees equals saturation temperature for suction side temperature, meaning that I'm going to subtract 20 degrees from my dry bulb temperature. Whatever that dry bulb temperature, and in our case it's 70 degrees, I'm going to subtract 20 degrees from that. That leaves me a saturation temperature of 50 degrees. Now, what does that mean? Right back to the same synopsis that we had on the high side, we're having on the low side. To be effective, I have to have that temperature change. Remember, it's coming in as an 80% liquid, 20% vapor, and I need it to be 100% vapor before it hits its compressor. Otherwise, we start having problems. So to do that, a 20-degree change in temperature from here to here will ensure that I have that capability happening. So now I know that my evaporator pressure or saturation temperature is 50 degrees. Again, I look at my card, I find 50 degrees, I move over to my right under 22 and it's 84.0. So 84 degrees. That should be what my pressure is reading. Now, you come over to the last little cloud and it says typical saturation temperature at compressor might be, and you hear that, you see that might be, all right, because remember 5 to 40 degrees, big range, but for demonstration purposes in the classroom and for the field, as far as getting a basis, 10 to 15 degrees is sufficient. So we'll say 15 degrees above the typical saturation temperature. Well, what's my saturation temperature? 50 degrees. I want to add 15 degrees to that. Now I have 65 degrees. So I go find it over here and put 65 degrees. Again, remember we go back to that the chemical reaction and the physics of temperature, pressures, and subtracting heat and adding heat. In the evaporator is adding heat. It's removing heat from the structure. That's where it begins to boil that refrigerant again. Well, if my saturation temperature is at 50, I know to be safe and protect my compressor, by the way that I'm calculating it, I should be reading the pressure or temperature on my pipe well insulated at 65 degrees. All right? So there's the whole format. Now we need to take all those typicals and move them back down into our conditions. We go back to our discharge pressure. We come up here, our discharge pressure for our typicals is 196. Saturation condenser temperature, again, it's 100 degrees because we use the PT card to convert it. The liquid temperature at condenser, we come up here, 85. The suction pressure, we come down to our low side, and it's 84 psig. The saturated suction temperature is 50. And the suction temperature at compressor, right here, which is 65. Now, again, you've got to repeat the superheat and subcooling process. We already know how to do that. We're going to take our 65 degrees and we're going to subtract our saturation temperature of 50, and I got 15. Our subcooling will work over here on the high side. The same process. I take the temperature, or my saturation temperature, in this case, which is 100, and I subtract my liquid temperature at condenser, which is 85, gives me 15. Now, minus whatever you get here in the compressor amps, outdoor fan motor amps, and the indoor fan motor amps. We won't deal with that, but right yet. In our last phase we will, and I'll put some erroneous numbers up there so you can figure out how to use that. But now we have all our numbers filtered out and placed in the proper position. Now here's what you need to pay attention to. All of what has been discussed to you in detail, you need to know. Not understand slightly. You need to physically know this inside and out. If your paperwork is not filled out in this manner so that I can look at it and see where you're getting your numbers, you will not pass that portion of that operation in the class. So please take the extra effort, do something neat, and put it in there so I can read that. And if there is a mistake, I can always come back to you and show you where the mistake was made. So don't take any shortcuts for any sake. So there's the form. These are all our numbers. Now you're asking yourself, why did I spend the last 15 minutes, 20 minutes going over all this? What am I supposed to do with it? That is going to be discussed in the next part. Welcome back. This is phase 3 of the exercise. Today, we're going to just overview of what we did in the other exercises or the other parts of the video. At this time, if you have any questions about this form, you need to bring it to our attention. We can't help you if you can't let us know that there's something wrong and you don't understand it. We're here to help you out. So please pay attention, understand this thoroughly, and let me know what the status is. Today, we're going to work in conjunction with this form and the troubleshooting chart. Now, you should have got this over at the bookstore. It's an easy, quick reference guide to troubleshooting. At the top, you'll see the refrigeration-side basic symptoms analysis. All right. Now, what this does is it's going to give you variables, and those variables will be determined from the numbers that you received off of this paperwork that you performed. So, let's have a quick overview. We know that we're dealing with R22. Now, this chart doesn't have anything to do with the type of refrigerant. So you can use this chart in almost any type of refrigerant. What we want to try to do is we're looking at our functional numbers here on this board. We can come down here to the conditions, and we're saying that the discharge pressure, remember the red is the typical. That's what it should be doing. In our case, it's much higher. It's 270 psig. So we look at our card. Now, in the classroom environment, you have to understand that because everything is not precise in a real environment, you're not going to get all 5 of these items across each time. Meaning that maybe if you get 3 out of the 5, that's more than likely the problem. In the real world, more than likely you'll get 4 or even 5 of them, right? But it narrows it down and it's a quick reference. I would suggest that you use this when you first hit the field and do that for, first 6 months. After that, it's going to become second nature to you, all right? But you can always have it on hand just in case you have one of those situations where you really don't understand what's going on, and it'll help you out. So let's just say that you look at your discharge pressure, your suction pressure, the superheat, subcooling, and the amps. Now remember yesterday we didn't fill out the amps, so when you go to your unit you're going to have to look at the sheet and find out what the amps for each one of these components should be running at. Now remember, that is when it's got a full load on it. So we're taking our discharge pressure, which we should say it's 196, and we got 270. Well, if I look down my discharge pressure, the first one, the arrow's pointing up, meaning that it's higher than typical. Now when we say higher than typical, if this number over here in the actual is 200, I wouldn't panic. But because it's 270, and understand I made it that way to make it look obvious, that's a problem. So your arrowhead in this line right here for discharge pressure is pointing up. That could mean that we have an overcharge system. If you follow this first column down, all you're looking for is what might be in the up position because it's talking about discharge pressure. Keep coming down, all the way down to the bottom. And you notice that at the bottom it says TXV feeler bulb loose. Well, we can alleviate that because we have a fixed situation here with our metering device. So therefore, it could not be that problem. So you can eliminate that right off the top of the bat. And then the next one that says high head pressure is poorly insulated feeler bulb. Again, we have a fixed. We don't have a TXV, so that can't be the problem. So those two right on the bottom are eliminated. Then we come down to our suction pressure, which in this case is 84, what we're really receiving, or what we should be receiving, excuse me, and what we're receiving is a low pressure. It's lower than 84. So then we come across here and we say, we thought it might be overcharged, but because the suction pressure isn't high enough, that probably won't be the problem. So now you got to look around and you say, well, undercharge, the suction pressure is low. The liquid restrictor, if it has a dryer in the system, that could possibly be a problem. And as you can see, you just go wherever it has a low evaporator airflow, all right, because of the suction pressure is below what should be typical. Now, you ask yourself, a low evaporator airflow, what could that mean? Could mean a dirty air filter. It could mean that the coils in the system are dirty, all right, the evaporator coils. A low outside ambient temperature. Okay, well, we know that that is not functional because it's 95 degrees out. So that's how you go about using this card. So let's go find superheat. Well, superheat is where it's supposed to be, all right? So we don't, you know, it doesn't fall in this card anywhere. And then subcooling is pretty low. So we look at subcooling and it says, undercharged could be a possibility. Dirty condenser could be a possibility. Now, even though that this is just a training environment, understand that in real life you're going to have more values actually show up here. On the paperwork drill, you may only have one or two. And what I'd like you to do is think about the process, all right? Use all your senses, use all the types of gauges that you need, and figure out these problems as you encounter them. And in conclusion, let's think about this process. We know that the two bottom ones here are not a consideration in this problem because we don't have the TXV at all. But up at the top, remember we had the discharge pressure high and I think it was a subcool was low, yes. All right. But it's one says overcharge, one says overcharged, and one says undercharged. Well, this is my general area right here that I'm concerned about. The only thing I'm really missing is my amps. If I had an actual amp reading, an example, let's just, for argument's sake, the unit's supposed to run at 16 amps and we have 10 amps. All right. So we're back up here at the overcharge and undercharge because our discharge pressure was high, our suction pressure was low, our subcooling was low, and in this case, I put 10 amps and the unit's supposed to run at 18 amps, then our amperage is low. So therefore, in this row, I have 3 items versus the 1 item under overcharge. So the possibility of my system being undercharged is more likely to be the factor in this situation. And that's how you have to address each problem as you go. Eventually, you're going to realize that it just comes second nature. You're going to start seeing certain pressures, certain temperatures, and it's going to go, oh, well, I already know that situation. But this is a real handy little tool to use to start off with. The other side of this is a real nice handy dandy, what I call the idiot wheel. It has this exact form minus all the information down here, but it has it right here for you. So if you're out in the field and you forget, at least you have something to go by, all right, to refresh your memory. And trust me, you know, everybody has those moments that happen more than we want to. And when it's 120 up on the rooftop, you could have a situation occur real quick. So all you need to do is know where to get the information. Now, this is a pretty simple process. The unit cycles on, meaning that the unit turns on, but for some reason something else happens. If you look, the internal motor thermostat kicks out, let's say. All right, well then you can look at number 18 and 19 and you turn your wheel in that direction. All right, and you can say high voltage, low suction. All right, that could be a possibility to your problem. all right, for the unit that cycles on. Low pressure switch, let's say your low pressure switch cuts out after a few minutes running the unit. Then you just turn it to 22 or any one of these numbers down here, and it'll show you what the possibility of that causing that problem is. So it's a very handy card. Be sure that you have this, you buy it at the bookstore, and it's very useful. Remember, never go out in the field without your TP card, this little idiot card wheel, and understanding this concept. It'll help you immensely. Especially here, we're going to drill you numerous times over it. It's going to be old school, but repetition is the only way that you're going to memorize this stuff. So we need your participation in it. Again, ask yourself, can I do this without the instructions? Do I know what all the terminology is? Do I know what it means for typical and actual and saturation temperature and discharge pressure and temperature and liquid temperature at the condenser? Do I understand how the system is working? What lines are discharged? Which one's liquid? Which one's suction? What three things happen in the condenser? It desuperheats, it condenses, and it subcools. If those three things don't happen in this condenser, nothing else is going to function correctly. The same thing in the evaporator. It evaporates and it creates superheat. If you don't understand that concept and how that compressor works, we need to talk, because you can't go any further, because all it's going to do is frustrate you. Remember, from this moment on, you're going to move out, and all we are is the homeowner. Hey, my unit don't start. I don't know why. You know, that's what I'm paying you the $85 an hour to solve. So, unless it's a safety factor, we want to see how you perform both under pressure, using your senses, using the equipment. For most of you, this will be the last class that you attend prior to hitting the street. Pay attention. We want you to be competent and confident prior to leaving this course. Thank you.